Okay, now we proceed to example 2 related to the Ampere's circuital law. Okay, the question is, consider an infinite filament cylindrical conductor of radius B carrying a current I with a current density J as illustrated in figure below. So this is the infinite filament cylindrical conductor. Okay, so it carries a current I with a current density J. This is I around the conductor. Radius R. This is radius B. This is towards the surface of Z. Okay, so the question asks you to determine the magnetic field B everywhere. Okay, the keywords is everywhere by using Ampere's circuital law. So, okay, when by using Ampere's circuital law is meaning that you need to use this law. Current enclosed equal to magnetic field strength dl equal to integration of current density surface towards surface. So the question asks you to determine the magnetic field. We know that the magnetic field is permeability times H, magnetic field intensity. So now we need to calculate magnetic field, this magnetic field in two conditions based on the range of the Amperean path radius R. So the first condition is inside the conductor, which is radius R less than or equal to B. The second condition is we need to calculate magnetic field outside the conductor, which is radius R bigger than B. Why we need to calculate inside and outside the conductor? Because the question asks you to determine magnetic field everywhere. Everywhere means that inside and outside the conductor. Okay. Okay, this is the first condition. Inside the conductor, which is R less than or equal to B. Okay, so we know that current from the equation, this equation, current equal to this integration of current density ds. So we will perform this first. Okay, so we know that this is vector. So when we want to change the vector include the magnitude and direction. So we can conclude that magnitude and direction is towards Z direction. This is Z direction. Okay, because the surface is dsz, so this is Z direction. Substitute Jz Az into this equation, you will get like this. Okay, so we know that dsz from table in the appendix is r dr dph az. Okay, r dr dph az. So you just need to substitute dsz here in the equation. You will get like this. So Az and Az can be removed because Az dot Az equal to 1. So at the end you will get like this, Jz r dr dv. So you need to do integration towards dr and dv. Okay. So dr is, the radius is from 0 to r. Okay. And v is 0 to 2 pi. Why 0 to 2 pi? Because this is, the surface is full surface, the v, full. So that's why it is 0 to 2 pi. So when we solve this equation, you will get like this. Current equal to Jz pi r squared. This is the first equation A. Next, you need to do the second one. This one. Okay. So change. So h, vector of h is hv av. Okay. Why this is v? Why this is z? Because this is towards surface. Surface is facing to the z direction. So this is dsz. But this one is length. Towards length. Length here is this length. Okay, this is the length. Okay, and the arrow is here. Like this. So dl. V. This is the V. Okay. So H is equal to HPAV. Okay. So substitute HPAV into this equation, you will get like this. And DLV, if you refer to the appendix, you will get RDVAV. So substitute inside here. So AV and AV can cancel out because equal to 1. So at the end you will get like this, HV R dV. So towards dV only. V is 0 to 2 pi because of the full angle, 360 degree. So the B equation, you get 2 pi r hv. So you get two equations, A and B. What do you need to do after that? You need to equating A and B to find magnetic field intensity. Equating both of the equation. Okay. To find the intensity, which is H. So, in order to get H, you need to bring 2 pi r to the left. So, this one will divided by 2 pi r. And then you will get Jzr over 2. Okay. We know that HV AV is equal to vector H. So vector H is equal to Jzr over 2 AV. Okay. So this is HV. Substitute into this equation, and we get direction here. So therefore, the magnetic field density, because the question asks you to find the magnetic field density B, is B mu naught H. So B mu H equal to mu H is here. This is H that we get from this one. Just substitute in here. Okay, this is the first condition. So the second condition is outside the conductor. This is inside. This is outside. the conductor, which is R bigger than B or equal to B. So we just need to repeat the same procedure except changing the range of radius as follows. So from the current, okay, the current here, the radius from previous is 0 to R. So here, for outside condition, the radius is from 0 to B. So we solve the equation, we will get jz pi b squared. Okay. For this one, we just need to change the range of radius for the first equation, density. For the first equation, current density. No need to change the radius for magnetic field intensity, because at the equation no need to integrate towards radius. So no new calculation for this part, because not involve the integration of radius. That's why we just take the same answer here, equation B. We just need to change the equation A. So equating both, this is equation A, this is equation A, this is equation B. Equating both equations to get H, you will get this one. Therefore, B equal to mu H. So generally, the magnetic field B can be expressed as this one. This is the first equation, this is the second equation. The first one is for R less than or equal to B. The second one is for R bigger than or equal to B. Okay, the difference is only here. B and R here. This one is don't have R and don't have the R is changed to B squared. Okay. This is the answer.